I will start with discussing the generic properties of ultralight dark matter. Then from these generic properties, there follow very simple things, such, for example, that ultralight dark matter should be bosons rather than fermions. And then the ultralight dark matter candidates can be classified according to spin, in a sense. Yeah. And then, of course, one starts with spin 0 with pseudo-Nambu-Goldstone bosons, and then with spin 1 with hidden sector U1 gauge bosons, which are the best motivated ultralight dark matter candidates. Now I will spend a lot of time on the Axion, because this, in my opinion, is the best, so to say, the best motivated ultralight dark matter candidate. So for the Axion, I will lead you through the whole concept. So we start with the phrasing of the strong CP problem or puzzle. Then I will present the axionic solution to the strong CP puzzle, derive or show the axion couplings to the standard model particles. We are looking into stellar energy loss constraints and constraints from conversion of astrophysical fluxes, from which it follows, in a sense, that the axion is really very light and very weakly coupled. Then we will consider also black hole superradiance constraints. And that, of course, we should also see whether, because this was the theme of the workshop, that Axion is in a sense an unavoidable dark matter candidate. So this will probably be the main subject of the second lecture, this Axion dark matter, and then also the ultralight dark photon. So this we will talk about tomorrow mainly. Now, very generic properties of ultralight dark matter. Now we have to let us consider the de Broglie wavelengths. That means the length 2 pi divided by the mass of the dark matter particle times the velocity of the dark matter particle. In our neighborhood in the Milky Way, so we have a typical dispersion velocity, and so let us consider this as a function as putting in numbers, so to say. So the velocity dispersion of the dark matter in the Milky Way is around 250 kilometers per second. And now, if we take now the mass of the dark matter particle, a milli-electron volt, then the de Broglie wavelength is about 1.5 meters, so 1.5 meter. So this is already quite a macroscopic scale. And then if one then puts in numbers in order to calculate the occupation number per de Broglie volume in our neighborhood in the Milky Way, then which is essentially so given by the number density of the dark matter particles, so the number of particles per volume times the de Broglie volume, the cube of this de Broglie wavelengths. So now we know that the number density of dark matter is, of course, nothing else than the mass density of the dark matter divided by the dark matter density. And as we have seen, so here this de Broglie wavelength scales with the mass and the velocity like 2 pi over m over v. Now putting in here numbers for a milli-electron volt dark matter particle, and taking the mass density of the dark matter, which we infer from observations, is from astronomical observations, which is 0.4 GeV per cubic centimeter cubed. Then we find for a milli-electron volt dark matter particle occupation number per de Broglie volume of the order of 10 to the 18. So it's really macroscopic thing. So this means first of all that the Pauli exclusion principle will exclude fermions as ultralight dark matter candidates. If I say ultralight dark matter is dark matter mass much less than 30 electron volt or a sub-electron volt scale, then so ultralight dark matter candidates are necessarily bosons. So this is the first conclusion from this very simple observation. The second observation, which will be very important then for the experiments Dimas will be talking about, is that ultralight dark matter is best described by classical waves. So he will, Dima will talk about many experiments where the wave nature of this dark matter is tested or is searched for. And so this dark matter can be thought of as waves of dark matter fields with the wavelengths with the wavelengths determined by the dark matter mass. So therefore, ultralight dark matter is sometimes also known as coherent field dark matter or as wave dark matter. Now, finally, if you now consider this de Broglie wavelengths, if you go to 10 to the minus 22 electron volt mass, then the de Broglie wavelengths will exceed the size of kiloparsec, of the size of dwarf galaxies. Therefore, ultralight dark matter particles must have a mass larger than 10 to the minus 22 electron volt. It's still a very small number, but so there is a lower bound and an upper bound in the mass, which is nice, and so maybe so this gives the range, so to say, for what we are talking about if we talk about ultralight dark sectors or ultralight dark matter. Now, so as I said, ultralight dark matter candidates, they must be bosons. So then it's of course natural to start with spin zero. And what are naturally ultralight particles? Naturally, these are pseudo Nambu-Goldstone bosons. So Nambu-Goldstone bosons arise from the breaking of a continuous global symmetry, and so as long as this symmetry is completely is exact, so to say, then the Nambu-Goldstone boson would be exactly massless. But if this symmetry is only an approximate symmetry, then these Nambu-Goldstone bosons can have a small mass if this is if this breaking is essentially small. And if these guys, these Nambu-Goldstone bosons, if they have a very large decay constant, then which is illustrated here. So if the symmetry breaking potential, so this kind of Mexican head potential has a huge radius and field space, then the interactions of these Nambu-Goldstone bosons with the standard model particles, they will be very much suppressed. This will be dimension 5 operators, and so they will be inversely proportional to this decay constant, and therefore, so this is also a very weakly coupled particle. We will later then learn how the dark matter is inevitably produced by the so-called misalignment mechanism. So this was spin 0, and then in spin 1, the simplest thing, of course, is you take a U1 gauge boson, a hidden sector U1 gauge boson, and if this is endowed with a small mass, and if it has a small kinetic mixing with the photon, that means if this dimension 4 operator involving the usual electromagnetic U1 field strength and the U1 field strength of this extra U1 gauge boson. So if this kinetic mixing parameter chi, or sometimes called epsilon, is very small, then this is also an ultralight dark matter candidate. And so tomorrow we will talk about this more.
Oh, we have a raised hand by Dima.
Yeah.
Yes, real sorry. Can you go back to this Mexican head just 1 second?
Yeah.
Sorry, this is an elementary question,
Yeah.
but
No
could you
problem.
quickly teach us how to read off the things you are talking about from this picture? For instance, the decay constant. How do we read?
So in a sense, so this we'll see in a few slides. We will see this for the axion. You read the decay constant is, so to say, so the number Goldstone boson is described by an angle, or by an angular variable, so to say, by the angle, and the angle. In order that you have an angle, you have to divide a scalar field by the decay constant, so to say, by the symmetry breaking scale, so to say. So this is an angular field variable which has a periodicity of 2 pi times the radius of this circle, so to say.
Thank you.
Yeah. So we start with pseudo-number Goldstone bosons as ultralight or dark matter candidates. So now, so the claim is that pseudo-number Goldstone bosons arising from the breaking of approximate global symmetries beyond the standard model at a scale much larger than the elegant weak scale are natural ultralight dark matter candidates. And during this lecture, so I will show this, how this arises at the example of the axion. But this can be general, all the considerations, or many of the considerations can be just generalized to an so-called axion-like particle or other number Goldstone bosons. So first of all, what are these approximate global symmetries, or what are nicely so well motivated approximate global symmetries? So there's, for example, scale invariance, and the corresponding number Goldstone boson was called the dilaton. There is the Peccei-Gwynn symmetry, which we will learn about in a few minutes, and the corresponding number Goldstone boson is called the axion. There is a lepton, it could be a lepton symmetry, which associated also with the introduction of Majorana neutrinos in the standard model, and the corresponding the number Goldstone boson arising from this breaking was called the Majoron, or there can be a family symmetry and the familon, and so on. But there can also be gauge symmetries, so more in a more mathematical or more general point of view. There can be the breaking of gauge symmetries of 10 dimensions can appear as the breaking of approximate global symmetries in 4 dimensions. And so these are the so-called, in such breaking, there arise these so-called type 2 closed string axion-like particles, or ALPs, and in this whole, the so-called axiverse is coming from this breaking of such gauge symmetries, and so their number reflects the, so to say, the topology of the 6 extra dimensions which are curved up after compactification. Now, and why are such number Goldstone bosons? Why are they natural ultralight dark matter candidates? Now, first of all, because they are from the beginning, so they are of course massless as long as the global symmetry exact, and a small mass can arise then from tiny, often non-perturbative explicit symmetry breaking effects. So like for the axion, it's really a non-perturbative effect where this arises. Second, the interactions with the standard model are suppressed by the large symmetry breaking scale. So this dimension 5 operators, they will involve this, they will be, so they will be suppressed by the symmetry breaking scale. And thirdly, and this is of course very important then for the dark matter, is that they will be produced automatically in the early universe by the so-called vacuum misalignment mechanism, which we will talk about in the next lecture. Now, I will illustrate now these 3 points with the axion. And it will be clear that this can be generalized also to other things, to other models. So what is the axion about? So the axion appears as a solution of the so-called strong CP puzzle, which I must start now. So now, if one considers the action of quantum chromodynamics, then we are very familiar with the gauge covariant kinetic term for the quarks, and also with the gauge covariant kinetic term for the gluons, or for the gauge fields in quantum chromodynamics. However, on the dimension 4 level, there is a third term which looks very similar to this gauge kinetic term. However, which involves, instead of just the contraction of or a summation of the gluon field strength tensor with itself, but here it's the gluon field strength tensor with its Hodge dual, so which is essentially in coordinates it's 1/2 times epsilon mu nu alpha beta g alpha beta. So this term, and this term, the strength of this term is determined by this so-called theta parameter or theta bar parameter. So I have taken out here, or conventionally one is always taking out a factor of alpha s over 8 pi, because in this case this theta parameter is just an angular parameter, so it can vary between minus pi and plus pi. So, and why is this the case? This is the case because the space-time integral of alpha s over 8 pi g dual is an integer, and this happens because of topological reasons in a non-abelian gauge series. So in a non-abelian gauge series, one has so-called instantons, and so this is an integer, and because this is an integer, this variable which determines the strength of this term is an angular variable. So, and this is the so-called theta angle. So this means, and the importance and the necessity that this term has to be included in the definition, so to say, of quantum chromodynamics is due to these gentlemen, so Bellamy et al., Geratoft, Kellen, Chaki, Ferretti, and so on. Now, so this means that that this theta angle, this theta bar, which can vary between minus pi and plus pi, is a fundamental parameter of QCD, in addition to alpha s and to the quark masses which are appearing in this thing. So then the question was, which arose very early in QCD, is how large is this theta angle? And so first of all, and then was the question, so how it could be observed? So so through which observations we could determine the size of this theta parameter. Now, to this end, one has first to remark that this topological term, this chi dual term, if you write it out now in terms of the color electric and color magnetic fields, it's just EA dot BA. This A is, of course, always this, it's going from 1 to 8 of the number of gluons, so to say. And E dot B violates time reversal invariance and parity, and thus CP. So this topological theta term will lead to flavor diagonal CP violation in QCD. And it was observed very early that the most sensitive probe of T and P violation in flavor conserving interactions is the electric dipole moment of the neutron. So if CP is conserved in strong interaction, then the electric dipole, the contribution of QCD to the electric dipole moment of the neutron should be zero, but it is now allowed because we have this theta parameter, and famous people like Di Vecchia, Veneziano, and Witten, they did the first calculations of this of the prediction of the dipole moment of the neutron. And nowadays the best determination is still the one by Maxim Pospelov and collaborators. So the prediction is that the dipole moment, the QCD contribution to the dipole moment of the neutron is linear in this theta parameter. Of course, it should be also it's linear in E times theta. And then there should be something which has the units of a length scale, and what is of course it's very natural to expect that the length scale is something like 1 over a hadronic scale. Now it's important to note here because of some of the chiral anomalies and so on. This effect should vanish if one of the quark had a zero mass, and therefore it's it's proportional, so to say, to reduced mass of the quarks. Now in two flavor QCD, it would be just mu times md divided by mu plus md. So if one of the quark masses would be zero, that this contribution would be zero. However, so if we know that it's not non-zero, it has a finite value, and so it's proportional to m star divided by the mass of the nucleon of the neutron squared. And so in numbers, you see it's about 10 to the minus 16 theta bar e centimeter. So the real coefficient has been calculated by Pospelov, but this is the order of magnitude. So yeah, so you would expect something like a 10 to the minus 16 e centimeter as a result from this calculation, if theta bar is of order unity. It can be between minus pi and plus pi. But the experiment said that the absolute value of the electric dipole moment of the neutron is less than 1.8 times 10 to the minus 26 e centimeter, which is a huge mismatch. So which means that now this theta bar experimentally is less than 10 to the minus 10. And this is the strong CP puzzle. Why is it so small? Of course, it would have been explained, for example, if one of the quarks has zero mass, if the up quark has zero mass, then it would be fine. There are kind of other explanation, but maybe the most elegant is the one of Pecci and Gwynn, to which we come now. So this is the so-called axionic solution of the strong CP puzzle, which can be summarized as following. So you should add to the standard model a Nambu-Goldstone field, which means an angular field. So it should vary between minus pi and plus pi. Should behave like a theta parameter. So it should be an angular field. And it can be written, of course, then also parameterized by a dimension one, mass dimension one scalar field divided by some dimension pool parameter, which we call the Axion decay constant. And this Nambu-Goldstone field, this should respect a non-linearly realized U1 Peccei-Quinn symmetry. So, which means that if you its action should be invariant, or its Lagrange should be invariant if you add to the field an arbitrary constant. So this is something like it should be really an angular variable, and this should be so you should have this this symmetry, and this symmetry should be broken only by the coupling to the gluonic topological charge density. So you want that this field couples linearly to this topological charge density, which is nothing else than alpha s over 8 pi g mu nu g tilde mu nu. So this is this. So it should really act. It should appear in the effective Lagrangian describing the dynamics of this field as a theta term, but now a space-time dependent theta term, because this A is a field. Now, so how does this solve the strong CP problem? Now, of course, now you have in a full Lagrangian of the theory to which you added this field is now the part from QCD, so which has this theta bar times Chi dual, but there is now this other this new term which is a space-time dependent. It's this Goldstone field, which also is proportional to Chi tilde. Now you can eliminate now, of course, you can just eliminate this theta bar by doing a shift. So you shift the field by this theta bar, and this was the only term which broke this symmetry. All the other terms by assumption are unchanged, and so you can really do that. But then, of course, now you have a theory which a Lagrangian which has a kinetic term for this theta term. The kinetic term is not changed, of course, if you do the shift, and still this field, this new field theta is still coupling to Chi dual. So now you have to show, in a sense, you have to show that this field has a vanishing vacuum expectation value. So it should be the vacuum expectation value of this field should be 0, which would mean that in vacuum QCD does not violate strong CP, does not violate CP. And this is the miracle, so to say, that the effect that QCD dynamics itself is solving the strong CP problem. So it was later, it was shown, so it was argued by different consideration by Roberto Peccei and Quinn already in these early times, but later it was shown in much more generality by the so-called Waffer-Witten theorem, is that the effective potential of this field of the field at energies below lambda QCD, so this would be has an absolute minimum at theta equal to 0, and thus predicts that the vacuum expectation value of this field is 0. There is no strong CP violation in vacuum. So this can be proven on very general grounds. But one can even derive an explicit formula for the self-interaction potential of this field. So in a sense, you have to integrate out the gluons in order to get the low energy effective field theory for this theta field. And this can be done using the chiral effective Lagrangian, because we know that the low energy QCD is described by the pion low energy effective Lagrangian. And so in a sense, by using this, you can determine the full dependence of the potential on theta. So and you find really that this potential is a periodic function, and it has an absolute minimum at theta equal to theta equal to 0. And you can even from this explicit expression, which involves the pion mass and the pion decay constant, and also the ratio of the up and down quark masses, which are about around 1/2. So you can take this formula and determine the second derivative around theta equal to 0, which is the mass of the excitation of this field. So first of all, of course, now you have this you have proven by this effect. You have proven that this introduction of this Nambu-Goldstone field solves the strong CP problem. So, and in a sense, it's at the end it's solved by QCD itself, because it says if you integrate out these gluons, which have these kind of interactions with this field, then the absolute minimum will be at theta equal to 0. Then there will be no strong CP violation in vacuum. But it also predicts, of course, also a particle, and this was missed by Roberto Pecce and Helen Quinn in their publications. They didn't talk about the axion. This was only found later by Steven Weinberg and Frank Wilczek, who emphasized that of course this solution of the Pecce-Quinn solution of the strong CP problem predicts the existence of a particle, and Frank Wilczek called it the axion because axion is a name of a cleaning detergent in US, and it's this particle wipes out or cleans a problem associated with an axial current in QCD. So this was the origin of the name of the axion. So we get from this solution, we get now that there is this particle excitation, the axion, and one can determine from this formula before, one can determine the mass, and indeed it's a pseudo Nambu-Goldstone boson, whose mass is parametrically suppressed by the decay constant, by this constant Fa, which is up to this point, which is only just so to say describing what is the periodicity of this field. So this is nothing more, but this parameter Fa. So if this is very large, if it's much larger than the electroweak scale, then we get a small mass for the axion. The axion is essentially given by a seesaw formula between the scale of chiral symmetry breaking given by the pion mass times the pion decay constant divided by this decay constant of the axion. So far, so good. Now, how can we get this from a UV completion? So what is the minimal UV completion to get such a dynamical theta field? So Roberto Pecce and Helen Quinn, they had a they proposed a UV completion, but this will give rise to a so-called visible axion, which has a decay constant of the order of the weak scale, and is completely excluded by beam dump experiments and all these things. So here comes now the minimal UV completion to get a dynamic theta field and to get a so-called invisible axion. And this was produced by Jeannie Kim and by Schiffman, Weinstein, and Zaharov. So what is the minimal addendum to the standard model is you add a singlet complex scalar field sigma, which features a spontaneously broken global U1 Pechet-Quinn symmetry. So this is supposed to have this this kind of Mexican head potential, and which gives rise to the spontaneous breaking of this global U1 symmetry, and you add, in addition, a vector-like colored fermion. So a vector-like exotic quark, so to say, charged also under this U1 Pechet-Quinn, such that the most general addendum to the standard model is, so to say, this kind of Mexican head potential. So this which has some self-interaction, quartic coupling. So here is the absolute value of sigma squared minus the symmetry breaking scale or the vacuum expectation value, so to say, for this Pechet-Quinn field VPQ, and the most general because now this is both sigma and this fermion are charged under this vector-like colored fermion are charged under U1 Pechet-Quinn. So this is the most general interaction which this new field has. So it has a Yukawa interaction with this Pechet-Quinn complex scalar field. Now, so this theory features after spontaneous symmetry breaking, which can now be after spontaneous symmetry breaking, you can now parameterize this sigma field by the radial field. So this is so to say the vacuum expectation value, and this is this is so to say the fluctuation in the direction perpendicular to the radius of this field. So this is the field, so to say, which is going in this direction. And then there's because I mean, this was a complex scalar, so you can take this radial parameterization. You take so to say the radius and the phase, and the phase is given we write as e to the a of x over v pq. So now, and this is so to say, this is the Nambu-Goldstone field. So this Nambu-Goldstone field is the excitation in this direction, or the excitation of the Nambu-Goldstone field goes in the angular direction. And here of course you see that this field has a periodicity of 2 pi VPQ, so to say. Now, the excitation of this angular field will be the Nambu-Goldstone boson, will be massless at this level, and the excitation of the modulus field of the field in the radial direction, the m rho, will be, so as we know this formula also from the Higgs mechanism, will be just the square root of 2 times this quartic coupling times the Pechet-Quinn BEF or vacuum expectation value, and the colored fermion will have a mass which determined by this Yukawa coupling times this Pechet-Quinn scale. Now, if you now integrate out, you can now integrate out this modulus, because it's very heavy, and we are interested now in the theory much below the symmetry breaking scale, the Pechet-Quinn symmetry breaking scale, but above the QCT scale, or above lambda QCT. Then, so to this end, you would just integrate out now this modulus and the heavy fermion. integrating out the modulus fixes, so to say, only the fields just the scalar field radius just to the Pecik-Winn scale and so on. But integrating out the heavy fermion gives a very important contribution now, because this was a vector-light colored fermion. If you integrate out now this fermion, then you get then you get essentially from integrating out this triangle graph, the heavy fermions. You get this dimension 5 operator, which exactly looks like a space-time dependent zeta parameter. So this is also related just to the chiral anomaly in this theory. So this is the dynamics of this angular field after integrating out the heavy fermion and the modulus. So it's just the kinetic term and this GT dual term and the linear interaction with this GT dual term and the dimension 5 operator interaction of this field with the topological charge density and QCD. So as I said before, if you have such a theory, so this was so to say the claim a few slides before. If you have such a theory, then the strong CP problem is solved. So because the QCD theta parameter can now be replaced by the dynamic field theta A of X or VPQ, and you immediately see also, of course, here that what we call the Axion decay constant in this theory and with this normalization is just nothing else than this Pecik-Winn symmetry breaking scale. And okay. So and this is already this is the simples, and now if this colored fermion would have also had a charge under the hypercharge U1, then you would have a similar by integrating out these things with two external photon lines. Then you would also get an F dual interaction already at the tree level in this effective Lagrangian, even before you integrate out the gluons. And this, so and again, in this term, there would be also a term, this would also involve A over VPQ. So I hope that Dima is your question now answered.
My question was a bit graphical, actually.
Yeah.
So it's answered, but I was just wondering, just by looking at that plot, you know.
At the plot, but at the plot, you can look at the plot, yeah, of course, as you said, the plot. This is the plot is this radius.
Sorry. Yeah.
The VPQ is this. So FA is the radius of the minimum, so to say.
Mm-hmm.
Okay. So now, so this was one particular example, but of course, this example can be generalized so we could have Axion. We could have other UV completions of the standard model, or introduce other models which after integrating out fields and so on give rise to the solution of the strong CP problem, to the axionic solution of the strong CP problem. So in generality, so to say, you can parameterize all these, so to say, the outcome after, or the effective Lagrangians or the effective interactions of the Axion couplings to the standard model below the QCD scale. Now, after integrating out even now this Chi dual term, you can parameterize by these most important interactions, which I have summarized here. They are all dimension 5. So they are all proportional to 1 over FA, so 1 over FA, 1 over FA. Or they are all 1 over FA. So which means that the coupling to the standard models are always suppressed by inverse powers of FA, and FA and the Petchy-Quinn symmetry banking scale are not always exactly the same. So it depends now on the effective number of something like the effective number of quarks contributing in this quark loop, which I call now a big N. But this in general, so this is the more general formula. And now, of course, then since the mass of the axion is inversely proportional to the decay constant, all these couplings above, they will be proportional to the mass. Now I will just talk a bit about these different terms. So the least model dependent coupling will be this coupling, which involves which is the Axion EDM coupling. So how it couples to the electric dipole moment of nucleons. And as I said, Maxime has calculated these coefficients CADN. So this is fixed. Has quite a large error still, but it's non-zero, so to say. And the experiments Dima will be talking about when he wants to use his Caspar electric to determine, so to say, axion to measure axion dark matter oscillations of induced oscillations of electric dipole moments. Then he's looking for this for this kind of interactions, which came originally from the Chi dual interaction, which we said before. Then there are the coupling to photons, and here is the coupling to the matter in the standard model. And this matter couplings, they are derivative couplings. And to photons, they look like the Chi dual term. And then there are, these coefficients, the Ca gamma and CAF, they are model dependent. So somewhat model dependent. The photon coupling is not so much model dependent. So there is one contribution. There's the one contribution arising from the mixing of the axion with the pion, but there's another contribution which depends on the ultraviolet completion and essentially the number of electric and or effective electric anomaly and the color anomaly. So, and for the nucleon couplings, there is also one contribution which are there are the contributions which are just model independent. They come just from the mixing of, again, from the axion with the pion, but there are other contributions which depend on the ultraviolet extension. And the electron couplings, they're completely model dependent. So
there is another raised hand.
Yeah, please.
Yes, thanks. So you pointed out that the coupling to the quark masses, I think it was, is a derivative. What does this mean as an effect? Or was it just that it's harder to calculate?
No, I mean, it's so first of all, this means, so to say, this shows that it has still, so normally the axion is a Nambu-Goldstone boson, so it has some kind of shift symmetry should remain for the axion, even after integrating on it. And this is, if you have a derivative interaction, then it's shift symmetric. So this is, so to say, this is a this is an important fact that the axion has to have this. One should be able to describe its low energy effective interactions as a derivative interaction with the matter fields. With the gauge fields, it's different because there are anomalies, and there could be so there the terms can be linear, so to say. And of course, with the electric dipole moment, it's not. But it's also very important for experiments which are looking for the axion dark matter wind. It's very important that this here the interaction. So to say, the axion velocity will play a role. Is this so? It's important also that these interactions with matter are derivative interactions.
Okay, I see. Thank you.
Okay. So then I want to emphasize or mention some of the constraints which really will show that this decay constant or this Petric wind symmetry breaking scale must be very large. So one yes.
Just to briefly indicate, we have probably 5 minutes or so.
Okay. Yes. That's good. Yeah.
Okay.
So first of all, so it was observed also in early times. Also, many observations have been done by Georg Raffelt. Yeah, is that the evolution of stars would be very sensitive to additional energy losses, in addition to energy losses due to the emission of neutrinos, So the axion or any particle emission could, for example, could for example delay the helium ignition and lead to an increase of the core mass, and this can result and such things can be seen if one is observed or try to be constrained if one is considering the Hertzsprung-Russell diagrams of globular clusters, and also the particle emission for horizontal branch or helium burning stars. The particle emission can reduce the helium burning lifetime, and that means the number of helium burning stars. And again, one could then compare the number of helium burning stars to the number of main sequence or red giant stars, and then give some things. So important constraints can be made on the axion by stellar energy losses. So the axions may be produced in stellar plasma by a Primakov process. So this is this effective, these two photon interactions, this F dual interaction which we have shown with a effective coupling Ga gamma, or by Bremsstrahlung. So by looking for the number of horizontal branch stars versus the number of red giants in the color magnitude diagram of globular clusters, and by the observation that this agrees with the standard model, one can give an upper bound on this Ga gamma, which is essentially alpha over 2 pi Fa. This is the electromagnetic fine structure constant, and a dimensionless constant A gamma, a dimensionless Wilson coefficient. This should be less than 6.6 times 10 to the minus 11 GeV. And so this is this limit in this plot, which you will see very often if you see axion, if you look for axion searches. This is the effective photon coupling, this Ga gamma in units of GeV to the minus 1 as a function of the axion mass. And you see, so this is the bound from horizontal branch stars. So everything above this line is forbidden, and this goes up to keV energies, which are the, so to say, the temperatures in horizontal branch stars. So second, so this other, so if you look, one finds that the brightness of the tip of the red giant branch in the color magnitude diagram of globular clusters agrees with the standard model. This gives a limit on this on the Axion electron coupling, which is conveniently parameterized by the mass of the electron over the decay constant times the CAE. And so here this is dimensionless. It's of the order of 10 to the minus 13, and it's indicated here. And the white dwarf luminosity function agrees that the white dwarf luminosity function agrees with the standard model, is also of the same order of magnitude, and is also plotted here. What you see in all these plots on these limits, which we are currently again updating for the review of particle physics, is that, of course, I mean, these limits are horizontal. They are independent of the mass in the wide range, so up to zero mass. While the prediction of Axion models like this KSVZ model or TFSZ model, they are linear, increasing with the mass. As I said before, yeah. They are just so the prediction of these simple models like KSVZ or DFSZ, they are just going linearly. So you see somehow for the KSVZ Axion model or the DFSZ Axion model, you get an upper bound on the mass of the for example by this photon coupling consideration at around 100 milli-electron volt, or here you get it at about 10 electron volt. But for the DFSZ Axion, which has a much higher, which has a 3-level Axion coupling to the electrons, you get an Axion mass limit of the order of 10 to the minus 3 electron volt. Then also from the duration of the neutrino burst of the supernova 1987A and temperature evolution of neutron stars, that it agrees with the standard model, you get also upper bounds on the nucleon couplings, which are of the order of 10 to the minus 9. They are similar normalized like that, like the nucleon mass over Fa times this coefficient Ca nucleon. And also from this you also get a limit on the effective coupling of the these are again the neutron coupling, and then also on the EDM coupling. So this is the limit from the supernova 1987A from the poor, if you just had this coupling. But in this case, so the normal QCD Axion is a very sharp prediction. So and you would need an additional contribution to the breaking of this shift symmetry, which I said before, in addition to the normal QCD Chi term, in order to populate this region with Axion candidates. It's possible, but we can discuss. We can talk about this in the discussion. So this is my last slide for today. So in fact, so what we see from the stellar energy loss constraints is that the Axion is really a very weakly interacting thin particles. It's very light and very weakly interacting because we have seen that its mass is or this this Fa or these couplings, they are constrained. And Fa has to be somehow larger than 10 to the 8, something like 10 to the 8 GeV in order to be viable with stellar energy loss constraints, which means that the mass should be less than a milli-electron volt or so. So this concludes my lecture today, and tomorrow we we continue with mainly with Axion dark matter, but also I review still a few other constraints, but the main subject tomorrow will be the dark matter, both for Axion and also for the dark photon.